Okay, thank you very much for the introduction. Also, thank you very much for having me here. I'm really happy to share some thoughts on impacts of climate change on water resources with you here today. So, I work with a research institute called Deltares in the Netherlands, and my job at Deltares is to support governments internationally in taking decisions and taking in water resources management, and in taking those decisions, taking climate change into account. And I like to share some of the ideas of what I encountered in my work with you today. So, if we talk about impacts and adaptation to climate change and of climate change on water resources, then it's really all about dealing with extremes and also with uncertainties. And this has always been the case, but of course this has been increased or is increasing due to climate change. A second thing that's really important talking about adaptation and water resources management is that we really need to think differently about solutions. So we need to think about solutions that are more robust and flexible to reduce the risks associated with climate variability and change. And it's also very important how to come from plans into actions. And every country has different cultural systems and different governance systems. But I think one message to leave here is that it's important that these systems of governance and finance are really meant to support a transition to a more sustainable water resources management. And to do this, it's very important to not invent new things, but really look for coherence with things that are going on already, with existing planning procedures, with existing procedures for investments, etc. So I will illustrate these messages using a few examples that I have encountered in my job. But first, let's have a look at the Earth. And we all know, we're all familiar with the astronauts coming back from the moon, and they had a look at our Earth and saw this small sphere looking very vulnerable. But yet this sphere, this Earth, is also looking very blue, containing a lot of water. But when we talk about water resources management, we should be aware that all the blue we see is not all the water we can manage, because most of the water is in the oceans. And when we talk about water resources management, it's really about talking about the fresh water in the lakes and the rivers. And if you look here at the drops in the picture, the bigger drop is representing all fresh water, and the very small drop is representing the fresh water that's available for water management, which is fresh water in lakes and rivers. So we're talking about only 0.3% of all the fresh water on the Earth. As I said, most of the other fresh water is stored in ice, and another 30% is stored in underground, in groundwater aquifers that can reach very deep. So, of course, this water is unevenly distributed over the Earth and over countries and river basins, and this is the process which is driving. This is what we call the hydrological cycle. And here, so we have precipitation, evaporation, ice, snow melt, which distributes water over the rivers, lakes, and also the groundwater. And this is, as I said, not a fair distribution over the Earth. So there are areas that are more dry and more wet over the earth. And climate change is amplifying this hydrological cycle and will cause more extremes. So on the one hand, you have this hydrological cycle determining the availability of water, and on the other side, you have Mark. And Mark is a colleague of mine who likes to drink cappuccino. And he uses a lot of water, but actually most of the water he is using is contained in the different products he's using, like the cappuccino, but also the water that's needed for manufacturing his car. So on the water use side, you see there's a very complicated picture. So it's not only about taking less showers, but it's also about a whole global trade system that is using a lot of water. And this methodology of calculating the amount of water a person is using is called the water footprint. So another sheet on this, so that's only the water that's directly used by persons is only 4%. The rest is indeed stored in products that we use. So as I said, climate change is going to impact these availability of water to the people. And I just took some pictures from your own climate change information for Chile. For Chile, this means that roughly it will be a little bit less dry, but much warmer in the north. It will be much drier in the middle part of the country, and it will be a little bit less warm in the south of the country. But this is just a comparison of what climate models are predicting with the current baseline climate. But the question, of course, is how well do we know our current baseline climate? Because, as I said, the climate and also the climate change will express itself mainly through changes in extremes. Just an example from my own country, the Netherlands. Last year, in January, it was the first time that all storm surge barriers that protect the Netherlands from storms had to be closed. This was the first time. Just a few weeks later, there was a high discharge of the River Rhine. And a few months later, in May, there were a lot of thunderstorms, and that gave big inundations in the cities. And then, after May, we had one of the worst droughts ever recorded, starting in May and lasting during all the summer. So just to give you an indication from my own country, and Chile, of course, also is having its share in the latest years, as was already mentioned a few times. The long record of droughts that's occurring in Chile, which is also causing that the reservoirs have large deficits already for many years. This is just a picture from 2015. And the question, of course, is this climate change or natural variability? And actually the answer is for designing and planning water infrastructure and managing water resources, it doesn't really matter. You need both of them. You need to take into account both of them in your planning and in your investment decisions. And if you look at what are the factors dominating your decisions from now in the next 100 years, it's not the trends of climate change that are dominant in your decisions in the first few decades, but it's the internal variability. So the variability of the climate system that is the most important to take into account. And of course, there's also other uncertainties like uncertainties in the tools that we use to support decisions, like computer models. So especially for precipitation, it's very important to first understand what's your baseline climate before you start even thinking about the trends caused by climate change. So to give you one example from the US, this graph shows the naturalized flow of the Colorado River in the US. And you know the Colorado River is an important river for water supply in the US. And here you see a record of the last 100 years, measured record. And back in 1922, there was an agreement signed, the Colorado Compact, in which determined the water allocation and distribution to the different states and to the different users. And as you can see, back then they only had a short record of 32 years to decide about the amount of water to be distributed. And what you saw happening afterwards is that the inflow went down quite a lot. And what's interesting is that through using paleo data, people have been able to reconstruct the inflow over more than 1,000 years back. And then we see that the moment they took this decision and make the agreement on the amount of water to be distributed to the different users, they were on a very high level when you consider the history of the river flows. So basically, they overestimated the water availability at the time. But what could I do at the time? Because there was not much more information available. So, and today, this regional climate is drying up, like the situation we had in Chile. Recently, they also had the same situation in California. So by assuming a fixed climate conditions when they designed their system, they now have to face the consequences of water not being available. So the question is, what could I have done differently? And basically, this question is also similar to what I was talking to people from the drainage department yesterday, and people were asking me, so how can I use this information? How can I design something that should function the next 50 years? What information should I use? How can I take a decision? And I think also another example is that also your water rights were also allocated at a time that the water availability was much higher. So what do we need? What is the solution? So I think the solution is basically in two words. It's robustness and flexibility. So we need to make our plans and our investments more robust. And more robust, I mean take into account a larger range of climate variability to design our water infrastructure. And flexibility, we need also to be able to adapt. If things turn out differently in the future, we should be able to take next steps that can increase the robustness. And one method to investigate this robustness is what we call a stress test. And the stress test it really starts with defining your desired performance. So what is the demand that should be met in a irrigation district, for instance, or what is the accepted damage when you designing flood protection system. So on the vertical axis of this figure, you see the performance, and these performance is always based on what stakeholders find important. So it's something to define together with your stakeholders. And in addition to the performance metrics, you can also define performance levels. So thresholds that of reliability, for instance, that should be met. And stresses simply means increase the temperature or the rainfall in mimicking the climate change that may come. So on the horizontal axis is basically increasing rainfall, increasing temperatures, and basically by stresses you really, for a larger range, you investigate how robust your system is, or if you plan for adaptation, how robust are your alternative strategies. And this process of stress testing, this of course should be based on sound science and data. So that's why we use hydrological models, water resources models, to calculate the performance of for instance, water distribution systems or flood protection systems. And of course, in doing this, you also need to include not only the climate stresses to your system, but also non-climate uncertainties, like changes in economy, changes in water demand, changes in population growth, people exposed to hazards, for instance. And this is just another example of a stress test, but this stress test has two dimensions. On the horizontal axis, the precipitation is increased compared to the current climate, and on the vertical axis, the temperature is increased compared to the current climate. And basically, the colors show your performance. In this case, I think it's the inflow to a reservoir, for instance, that should be on a certain level. And with the colors, you can indicate what are desired, what are desired and what are undesired conditions. So the stresses is part of a family called bottom-up vulnerability approaches, and we have applied one of these methods also in a pilot basin in Chile for the Rio Limarí. And this is a part of a methodology called CRIDA. And CRIDA is basically telling you how you can do a water resources planning process and how to incorporate climate in your risk analysis, but also how you can plan flexibly to cope with future climate changes. So I'm going to highlight just two steps from this methodology. First of all, so the Limarí River, there's a large agricultural community there. There's some industry and some population centers there that are dependent on the River Limarí for its water supply. And together with Casallac and Promra, a model was being built that could simulate the water distribution for this area. And this has been used to stress test. So we increase or decrease the amount of rainfall available to the system, and we increase the temperature, influencing snow melt, for instance, in the Andes. And we also discussed with the stakeholders what do you find acceptable performance. So they came up with two performance metrics. One is the inflow to the reservoir, so how much water is being stored in the reservoirs in the area, and the other performance metric was the unmet demand. So that, of course, you want to keep that as low as possible. Well, the outcome of the stress, as you see in the lower left panel, and there it shows that there's a line in the middle. This is basically this performance threshold beyond which people thought the performance became unacceptable. This means there was not enough water to bridge the gap of a 3-year drought. That's basically what it says. And all the dots you see in the figure represent climate change projections of a lot of different models. And basically what you see there is that most of the dots and most of the model projections are on the left side of this acceptable threshold, meaning that about 75% of the models say that in the future, for this system, Lima Reef system, it will be too dry to meet the performance, acceptable performance. So that basically we use this information to go to stakeholders and ask for their perception. Do you think this is a high impact or low or medium impact? And they classify the impacts as high and medium. And of course, then the next step is what can you do about it? And that's we collected in this study a lot of potential actions that could be taken from interviews and during a workshop, from local surveys, but also we looked into different governmental plans. And I think that's also important in adaptation. Don't think too traditionally. Don't stick to the solution that you already know, but also look further ahead and to other solutions, both on the supply and the demand side. And so there was a list of solutions identified. And again, these solutions were simulated by the model. And we can then again test if the acceptable performance was improving, yes or no. And in the end, there was a list of measures, individual measures or measures combined in packages that gave some reduction, some improvement of the performance. And so that's to make the system more robust. And we also looked at what are measures that are more desired that you can take first, and what are measures that are going to be harmful in other ways that you can wait for and postpone and take later. So in this way you design also what we call adaptation pathways that can guide you in what measures can be implemented directly and what options do you have if the climate gets drier in the future. And now an example from the Netherlands to conclude. In the Netherlands, you wouldn't expect. It's a country of polders and a lot of water and flooding. But as I indicated before, we also have some limited drought problems, because I don't want to compare our drought problems with Chile. So here is a picture showing our basically our water system. So we have two main rivers entering the country, the Rhine and the Meuse River, and floating to the western areas and to the northern area where there's a large basin called the IJssel Lake. And on the right panel you see that during the summer months we have a precipitation deficit growing in the Netherlands. And the problems we have with droughts is that during the summer months the groundwater is sinking, groundwater levels are sinking. The buffer, the big lake, is too much water is being drawn out. The rivers, the water level is getting too low for shipping, and because of the low flows of the rivers, also salt water is entering the country from the seaside. So these are basically the problems encountered with droughts in the Netherlands. And we have a system which is really engineered and pretty good manageable. It's pretty good in managing and allocating the water to the different users. So we have the main system of rivers, which is connected through sluices to a regional water system where most of the users are. And how is this system being governed in the Netherlands? How is it managed? So to say it in contrast with Chile, this is more like one connected system. In Chile you have a lot of different basins that are not connected. So there's a difference there. But how do we manage this? So we have, like I said, a physical system that is able to redirect the water to the different users. We have agreements between the different water users and parties. And we have, on a national level, decided on basically rules and standards how to distribute water. And this is what you see on the lower left side. We have basically 4 categories of water use. And the first one is the category that if they don't get enough water, you get irreversible damage. So it's vulnerable nature areas, it's soil subsidence, or it's the dikes. If they get too dry, that in some parts of the country that's also can lead to irreversible damage. The second category is the public utilities, and then only at the third category we get some high economic value commercial use, and the lowest, and the last category 4 is all the other functions like shipping, all the other agriculture and economic use and nature. So there's a priority order in which the water is allocated during periods of droughts. And when we have these periods of droughts, there is also an emergency organization which is coordinated nationally that decides on allocating the water, but also informs all the water users what's going to happen. So this whole system is really supported by a lot of data and models on a national scale. And of course, looking at climate change, we also have a process designed for planning in which the regions and the national government cooperate. And also this program, which is called the Delta program, has flexibility as one of the main core principles. What you can see on the lower left side is that we have 3 periods in which actions can be taken. So we have the actions that can be taken on the short term, which are being implemented at current. Then we have measures that are options for the middle long term, and then we have options for the longer term. So basically, this also represents an adaptation path that could be followed. And there are 2 paths: either the region and the water users take actions, or on the national level and the national water system, infrastructural measures are being taken. So it has both the governance levels of the national and the regional level in it, and it has this flexibility of implementing actions for the short term and already having investigated the options for the longer term. And of course, this adaptive strategy is quite challenging, and one of the most important things to do is to monitor. So monitor how effective are your measures, but also monitor how is the climate changing, and when should I take a next step and the next decision. Okay, I think then I finalized my presentation. I had a few other slides, but I'm going to finalize. So I just wanted to show you this national Dutch approach to climate adaptation and drought management. And it's of course very different from your system, which is it's more based on a water market. This is just an example of a water market which is being applied in Australia, another country that uses the same system. And of course, this water market helps to, with higher prices during dry conditions, to steer the use of water. But of course, there are also some strengths and weaknesses of this system. And here you see a summary of what I found in Australia, of the strengths and the weaknesses of the system. So I'm going to my last slide to conclude in time. So to conclude, it's very important to have a very profound understanding of your variability when you're going to plan and design new water infrastructure or adaptation measures to manage your water resources. The actions you take should be robust or flexible, or robust and flexible, to be able to cope with the climate uncertainty in the future. And the institutions that you build around it, they should be helpful to make a transition, to make implementation happen, and towards a water system that is more sustainable for the future. So thank you for your attention.